The V3Si structure is formed on the body-centered cubic base of silicon with an additional 2 vanadium atoms on each face, creating orthogonal chains. The space between 2 vanadium atoms is half the lattice length, even shorter than in pure vanadium crystals, yielding higher electron density in the Fermi level. The electric conductivity is therefore even higher than regular metals with a band gap of 0. At low temperatures, the cubic lattice may soften, extending several percent into a tetragonal lattice as a result of the strained vanadium-vanadium single bond. This is a martensitic transition with a very little change in the unit cell volume and total energy, therefore not affecting the crystal's critical temperature significantly. Vanadium has an electronegativity of 1.63, whereas silicon has an electronegativity of 1.9. The low electronegativity difference leads to metallic bonding, where electrons float around almost unbound. The band gap is therefore 0, similar to other metals, creating high electrical conductivity. The V3Si phase is created by either thermal diffusion of silicon into vanadium or cooling of mixture of 25% silicon and 75% vanadium. Diffusion is more favorable as the region with excess vanadium can still exist as V3Si. The phase falls between 19 and 25% silicon with congruent melting point, where the composition of both solid and liquid is the same, is about 1920 Celsius. V3Si remains a single phase at a wide variety of temperatures, with its phase extending for most of the vertical portion of the diagram. Notably, most of the other states within the vanadium-silicon phase diagram are not single phases. This implies vanadium and silicon are not miscible in each other except for certain compounds. The primary defect within the V3Si compound are intrinsic point defects called antisites. Antisites are defects within a compound involving 2 or more elements at swap positions. In this case, the silicon corners are replaced with vanadium. Antisites are the primary defect because of its low enthalpy of formation. Compared to other point defects such as vacancies, antisites dominate. However, the other point defects still are present, just not in abundance. The single phase of V3Si permits antisites with excess vanadium, minimum of 75% vanadium and up to 81%, without phase segregation, remaining in a single crystal phase. In this metallic compound, the primary mode of mass transportation occurs through collision cascade or displacement cascade. Due to V3Si being an A15 compound, the high electron density increases the probability of these energetic collisions that are induced by an energetic particle. In the solid compound, an atom within the V3Si compound is displaced by an incident damaging particle, which causes additional displacement similar to the butterfly effect. V3Si is also a superconductor, where normal metals have resistivity decreasing to certain values at 0 Kelvin. This happens at abruptly above 0 Kelvin for V3Si. Conductivity will go to infinite at realistic temperatures, and all magnetic flux fields are expelled from the material. The temperature-wise stability of V3Si, along with a high critical temperature, makes it commercially competitive. The transition and the non-transition elements are most promising. They were economically the most viable and metallurgically very favorable within its place in the vanadium-silicon phase diagram. The V3Si phase is unique as a single phase. Its bonding structure and defects allow it to have superconducting properties, thus making the phase exotic.